Okay. Hi, good morning, everyone. I'm Nick again, and thank you and welcome back to our Princeton Center for Complex Materials Summer School on Condensed Matter Physics. And as you all know, our theme is magnetism and quantum materials. So today is the day that was supposed to be the talks for Wednesday. We have Professor Joe Checkelsky from MIT and Professor Leon Balance again, 3 talks today. So thanks again, everyone, for participating, and we hope you enjoy our program. I sent out an email this morning about a survey to kind of let us know about how things have been going this year, the virtual summer school. And if you could please fill that out when you get a chance, that would really be great for us going forward. So I had the pleasure of introducing this morning Professor Joe Checkelsky from MIT, whose lab is really specialist in all kinds of interesting quantum materials, kind of combining topology and correlated electron systems and magnetism and all kinds of things on the forefront of condensed matter. He's a great presenter with a great history of doing really cool science. And we're really lucky to have him presenting for all of us this morning. Professor Checkelsky's talk is going to be about magnetism and quantum materials, more specifically magnetism and topological materials. So without further ado, I'd like to present Professor Joseph Checkelsky.
Okay, thank you, Nick. Let me see if I can figure out how to share my screen, which I have, I think, and then I will go into this presenter view. Hope everyone's not too dizzy with the animation. So let me start by thanking Nick and all of the organizers for putting together what is a great summer school, and especially I think probably as many people have noted, managing to make it all come online and come earlier than originally planned. I think it was a heroic effort that I really appreciate, and it's my pleasure to take part in it. So what I would like to do with the time I have today in these 2 lectures is tell you about magnetism in topological materials. And I hope that there will be a lot of overlap with what you've heard from some of the other speakers, whether it's in topology or magnetism or other concepts. And what I will try to do is present some of those same ideas, but maybe from a little more material-centric point of view, just to give you another way of thinking about these problems. And this is a particular example, the details, of which I will try to get to by the end of the talk, which is going to be, I'll try to give you an example at the end of how you can use some complex aspects of crystal structure. This is a particular material which has a screw axis, and talk about how we can try to use things like a 4-1 screw axis to intermingle both magnetism and topology in a real system. And hopefully it'll make a little bit of sense by the time we get there. If we can ever get back to going into offices again, if you want to play around with this kind of thing, come to my office in building 13 at MIT, and you can enjoy crystal structures in VR. But anyway, so let me give the 1-slide introduction to what I see as a way to think about quantum materials in terms of just a broad research view. So don't worry, my whole talk won't be this broad, but I want to start it this way. So what is the field of quantum materials? So it's a research field like many others, which is really interested in the concept of emergence in a complex system. So if this was like a biology talk or something like that, the way you might articulate this idea is to say that, you could in biology understand one single cell really well, but you wouldn't be able to guess from that one single cell that if you put 30 trillion cells together, that it would walk and talk like a human being. And that emergent behavior is extremely interesting. So, okay, in the context of quantum materials, the analogy would be you could understand one atom, say, of lead very well, but you wouldn't guess that if you could put 10 to the 23 lead atoms together, that it would make this quantum condensate, which would conduct electricity perfectly as a superconductor, right? And so nor, for example, if you looked at the periodic table of the elements, would you guess that, oh, these different elements would have different superconducting transition temperatures. Some of them would need pressure to superconduct. You could combine the elements into different materials that, for example, under extreme pressures could superconduct at a near to room temperature recently. So it is this kind of variety of systems and surprises that come out, I think, that really drive interest in quantum materials. And if you want, the phase space that we're working in from this material-centric view is basically the combination of the periodic table with the symmetry allowed ways that we're able to arrange those atoms in crystals. And just to give you sort of a preview of what magnetism can bring, there's around 230 of those so-called space groups which are allowed in crystals, and about an order of magnitude larger when you bring in the magnetic degrees of freedom. So what is magnetism? How does magnetism fit into this context? So magnetism is a quantum mechanical phenomenon, right? So it's not something that you might believe when you're growing up that it's connected to this unusual world of quantum mechanics, but it's really related deeply to the Pauli exclusion principle. And the idea is that basically electrons, under the right conditions, can lower the energy of the system by having their spins aligned in the same direction, because it can reduce the Coulomb repulsion between electrons, right? And so the amazing thing that this quantum mechanical thing can happen at these very elevated temperature scales. So this is someone from the MIT demo office showing how you can take a torch to a nut which contains a lot of iron and turn the magnetism off at its Curie temperature, right? So it's this incredibly robust thing, but then amazingly, something that's very unique about magnetism is we can manipulate magnetism with much lower energy scales. So this picture in the bottom left-hand corner is showing the magnetic reversal of a film of nickel. And it's only a few hundred Ørsted of a magnetic field, which is a very, very small magnetic field that is able to reverse nickel's magnetic order. And the key point about this and sort of this ferromagnetism more generally is that when you're reversing nickel, you're not destroying the magnetic phase, you're just reorienting the magnetic moment. And it is that basically a different physical energy scale controls the orientation of a magnetic moment, whether it's a local crystal electric field or spin orbit coupling. It allows you to take this robust quantum mechanical thing and move it around if you want. And then at the same time, something else that's also important is that despite the fact that you have all of this exotica happening with the spin degree of freedom, by and large, simple ferromagnetic metals still behave like metals, almost like some non-interacting gas of electrons. And so you can actually still think about metal physics even with all this that's going on underneath. And so what I'm going to do over the course of these two lectures is talk about bringing this, simple concepts of magnetism to a little bit more exotic electronic phases and thinking about topology and then what we can build from those into more exotic fundamental ground states and also potentially devices. So let me give you an example, though, pardon me, of what you might be able to do with these magnetic systems. So this is an example of something that was discovered in the 1980s called giant magnetoresistance, which really leverages these unique aspects of magnetism to do something very new and exciting. And what was done in the 80s was people realized you could make these little sandwich structures of magnets. Here you have sort of one magnetic layer separated to another magnetic layer by some spacer. And what was found experimentally was the electrical resistance of these little sandwiches was very different if the magnetic orientations were the same or opposite. And so this was interesting. It was a so-called giant response. This electrical response was so big. And how this further leveraged magnetism was the realization that in these magnetic structures, they're very robust. If you make them out of the right materials, they can be magnetic at far above room temperature. But because of that acute sensitivity to external magnetic fields I referred to before, you could bring this little structure down near, for example, a strip of little magnetic bits and use it to sense the local magnetic orientation, because this so-called free layer could flip in the presence of the local magnetic bit, and then you could detect that electrically by seeing the change in resistance, right? So this seemingly a simple concept was actually a very deep breakthrough. And it basically led to this exponential increase in the storage density of hard drives, which use this technology to make these bits and the read sensors smaller and smaller. And so it leverages quantum mechanics, which is happening at room temperature or higher, with this controllable aspect that I was mentioning before. And that if you needed any further sales that this is interesting, one way of looking at it, it was sort of a PRL in the 80s. It made it into hard drives in the 90s, won the Nobel Prize in 2007, right? So I think it sort of give you some example of the excitement that can happen in condensed matter when we really can understand deeply these quantum mechanical aspects of magnetism and then put them to use. So the concept, though, that I want to talk about, that I want to marry this idea of magnetism to, and I hope you've heard a lot of this already before, is something called topology, which is a relatively new concept in the condensed matter physics, but really follows the grand tradition of physics, where mathematics is either borrowed or invented to understand different kind of physical phenomena. So you could go back to Newton, basically Newton or Leibniz, if you want, inventing calculus to do kinematics of different kinds. Recently, and actually it's been going on for a while, people have been borrowing higher and higher level concepts of topology into physics. So having said that, I think that the concepts from topology that we'll need for my presentations are really the most basic. And I found these outlined very nicely in this book that I pulled out of the math library at MIT. And it's a book from the 60s called Experiments in Topology. So you might not be surprised that it's from the 60s. It's not making topological insulators or whatever it is that I want to talk about. It's really talking about how to understand topology by, for example, using paper and scissors to cut different kind of objects like Klein bottles. So having said that, even in the first chapter of this book, it outlined the concept which I think you need to be able to grasp the things I want to talk about, which is that it had this passage that said a topologist is interested in the properties of a thing that, while they're in a sense geometrical, are the most permanent, the ones that will survive distortion and stretching. And the idea is that here with the Klein bottle, or you're more familiar with a Mobius strip, the notion is that that kind of object, that the twist, to say, associated with the Mobius strip doesn't care if you move around the Mobius strip a little bit. That aspect, even though maybe you change the angle of the paper or something like that, if it's a paper and scissors Mobius strip, that doesn't alter in any way the deeper topology associated with how many twists you have in the Mobius strip. So there are some conventional examples that people give. So I think that the most common is to talk about the number of holes an object has. So here there's a woodworker who's drilling holes in a ball. And the idea is that in the before phase, before a hole is drilled, even if he scratches the ball with his fingernails, it only makes some superficial dents, which doesn't change the number of holes. And the object only has a topological change when he's really drilled all the way through. And sort of some related concept is there's nothing like half a hole. And so you basically have this object and this object in different topological classes. I think a maybe more illustrative example is, again, this is maybe what some any ways would call a Mobius shawl. And basically in the crocheting process of making this shawl, there's this key instant here where you twist the shawl and then continue to finish making it. And in that process, you encode this twist in the shawl in such a way that it cannot be removed unless you sort of rip the shawl apart, right? And so these are more mathematical or a geometric way of looking at the problem. But to give you the broad view that really excited the condensed matter physics community and others was that the notion that there could be some analogy between this behavior in math or geometry and then in, say, for example, the electronic properties of solids. There could be some kind of robust electronic aspect of solids that could, for example, either encode some electronic mode, maybe encode information, right? And that has really driven a lot of interest recently. So you don't have to take my word for it. So this was this part of this, anyways, was awarded the Nobel Prize a few years ago for these theoretical concepts underpinning this idea. And for example, that was illustrated by the Nobel Committee, showing this map between the math world, where you have geometric objects, which are all the same in terms of the number of holes until pow, you make one hole, or pow, you make a second hole. And there's some mapping between that and then the world of electronic materials, where, for example, the ability for things to conduct electricity was similarly quantized in some stepwise fashion. So this, I think, was a little bit more for the general public. So they didn't use, I think, a real object which has quantized conductance. But I will introduce that in a moment. But just to say, again, the reason that this was exciting was that these topological materials might be used in the next generation of electronic superconductors, future quantum computers, that we might really leverage these things to do something new. So I think the example that they were alluding to in the previous slide in terms of this stepwise quantization of conductance, pardon me, is the so-called quantum Hall state. So in the quantum Hall state, most conventionally, you have a two-dimensional sheet of electrons. And to this two-dimensional sheet of electrons, you apply a magnetic field that's coming out of the page. And this is a very semi-classical picture, but just to give you some intuition, the idea is that electrons spiral around the field lines, those that live sort of in the center of the sheet, and really cannot contribute to moving charge from one side of the sample to the other. And it's only those that are near the boundary, which make, in the semi-classical world anyway, this so-called skipping orbit, which can move charge around. And there's two different interesting aspects, at least, to this motion of the charge. One is that it's chiral, right? So it has a handedness, which is set by the direction of the magnetic field. But the other is that it is robust in the sense that even if I were to disorder the edge, take a blade and cut part of it, I would never remove the fact that there could be an edge in the system. And therefore, the notion is that this boundary mode could continue moving around the edge and would be insensitive to disorder. So the way that this was measured in the most conventional way was looking at the electrical transport through such a sheet. So here the sheet is just laid down here on the plane. The magnetic field is applied in the vertical direction. And then this is, I should have given a reference to Wikipedia, sorry, where I pulled off this image. But the notion here is in red, for example, this is showing you the electrical resistance. And the amazing thing that happens is for certain values of the magnetic field, the resistance appears to go to zero. And it's at those conditions when the charge is being carried by these dissipationless chiral modes. There's no dissipation in the sense, for example, there's no mode for these guys to scatter into to move in the backwards direction. So what's even more amazing about this experiment is if you measure a voltage across the sample, you measure a quantized value, quantized in the sense that it's related to h over e squared, and it's basically some integer multiplied by this. And what I'll show you in the next slide is what it's doing is basically counting the number of these chiral modes. So it's showing you the different staircase levels that were on the previous slide. So to finish this mapping, so what is the idea again going between geometry and these topological modes? So the analogy that one could give was that, well, in the world of geometry, you could characterize different geometric objects by their genus, or this number of holes. Mathematically, you can calculate that through something called the Gauss-Bonnet theorem, where you integrate the Gaussian curvature. So I will just sketch for you the idea without getting into any of the great detail. I refer you to these historically important papers, is that there is a similar idea in the world of electronic structure, where again, you're calculating some geometric quantity, but you're integrating over the momentum space information of the electronic structure, and it's something associated with the electron wave function that you integrate. In much the same way that this integral is quantized in terms of the number of holes, this integral is also quantized. And if you hop over to real space for these two-dimensional systems, it gives you the number of these edge modes, right? And so then the idea in these quantum Hall systems is that number of edge modes and their ability to have this quantum Hall conductance, for example, is insensitive to disorder, if you add some charge disorder or something like that, right? So this it was all physics, which was developed and understood in the 1970s and the 1980s, and is extremely important. If I just try to summarize, again, the picture is something like you can make the so-called topological phase by having a two-dimensional electron gas to which you apply a magnetic field and get these edge modes. But there was a tremendous amount of progress in the 2000s when it was understood, building on works of Haldane, Kane-Millay, and Bernoulli-Hughes-Zhang, that you could do the same kind of thing in a lot of different ways, and in particular without necessarily needing an external magnetic field. So one of I think the first example of this, which was it was proposed and realized without an external magnetic field, was the idea of so-called topological insulator, which you can imagine in a lot of different ways. But the way I think it might be most intuitive to think about it is it's basically this, it's related to this quantum Hall phase, but instead of having an externally imposed magnetic field, you're using a kind of internal magnetic field to a material. And the idea is that typically these materials are made out of very heavy elements. And so if you look at something like mercury or bismuth or some very heavy element, if you really were to be able to examine the electrons which are moving around the core of the nuclei in those systems, the potential well is so deep that those electrons are moving at tremendous speeds, some fraction of the speed of light. And so in the reference frame of those electrons, the ionic core is moving around extremely quickly and generating, if you like, then some kind of internal magnetic field that charge would feel. But the fact that these systems are supposed to be non-magnetic, they have time reversal symmetry, means that if you have that kind of behavior for one spin of the electron, you have the same kind of behavior for the opposite spin, but it should be in sort of a counter-propagating fashion, such that these topological insulators get these boundary modes, but they're helical rather than chiral. And actually this notion that you have time reversal symmetry, or that they're not magnetic, is really what is important for their topological protection. So this was a theoretical concept that was borne out by experiment very, very soon after it was predicted. So this is how it was done in 2D. You had a 2D insulator with a boundary mode, and that was detected in this case by measuring the conductance of this system and finding that under the right conditions, when the material was grown in the right way, that when you would tune you have some tuning parameter, you would tune to the condition where you should only have these edge modes. You found indeed you had some quantization of the conductance. But again, and I think this is a real hallmark of this subfield, is that from one idea come many related and beautiful concepts. It was soon realized if you could do that in 2D, why not do something similar in 3D? And in that case, you would have a 3D insulator, this kind of bulk insulator, but it's wrapped with an interesting kind of 2D mode, on its surface. And again, the idea here, much the same way that disorder wouldn't be able to ruin this edge mode, disorder on the surface wouldn't be able to open, say, a gap in this spectrum. And that was something that was borne out using these different spectroscopic techniques, where basically what people were able to see in these different heavy element small gap semiconductors is modes which were attached to the surface had this linear-ish spectrum, which they should at least near to this crossing point, and basically didn't have a gap, right? And the idea that this was predicted by time reversal symmetry, and that was giving what people refer to as a topological protection, meaning that you could move around the shape of the band a little bit, but you weren't able to open a gap. So That was an introduction, by the way. It took a little bit longer than I was planning. But my plan now for the lecture this morning is to talk about what happens when you introduce magnetism into different kinds of topological systems. And I'll start this morning with putting magnetism into just that thing I was telling you about, a topological insulator. I'll spend a little bit of time at the end talking about topological semimetals. And then the lecture this afternoon will be about magnetism in so-called topological metals. And I'm told, by the way, that you guys can ask questions at any time. I know it's tough to do so, you know, in this format. If you do have questions, I'd love to hear them. I was talking with the organizers before. You know, giving these talks remotely can feel a little bit like shouting into the wind. Sometimes you really don't know if anybody's hearing you. Anyways, if you have questions, I encourage you to ask. So, okay, so then let me then repose the question and then try to answer it for 15 minutes or so about what happens when you combine magnetism and different kinds of topological materials, in particular, a topological insulator. And so one question you might have, given the way that I set up what a topological insulator is why on earth would you want to combine magnetism with a topological insulator? I mean, I said that, for example, for a 3D topological insulator, this interesting surface mode, which you could look at in real space or in K-space, is protected by time reversal symmetry. So if you make something magnetic and you lift time reversal symmetry, might not you get just some boring or useless thing? The answer to that question is, at least under the right conditions, no, you're not left with something boring, at least if you do it the right way. You can open a gap in this surface spectrum, but what then resides, or what appears, is a new kind of topological state, which is characterized by, here I'm trying to depict a one-dimensional edge mode, which is very much the cousin of the quantum Hall effect, but say driven by this kind of magnetic order. So how would you do such a thing? So here is where I'm going to pivot a little bit to try to give you guys a little bit of the materials flavor and development, the way it worked in this field. I think not only is it whatever historically important, but it can give you, I think, a real taste of how a field develops, and then therefore how you might apply similar kind of methodology to new fields, right? So actually, this idea of making a topological insulator magnetic had been explored in a material. Oh, Nick has a question.
Yes, hi, Professor. We have a question from the audience, which is, is it always necessary to have strong spin-orbit coupling in order to get a topological insulator?
So it is only one way. And so I think the thing that I was going to skip to, that I can skip to at the end, and I can show you, is that no, there are sort of myriad different ways for making a topological insulator. The original proposal that you could have a topological insulator was based on a model of graphene. And there, you know, people thought experimentally, you know, the challenge in realizing that was that you have very small spin orbit coupling. But in principle, it's even true that for graphene, where you have you have a band crossing point, which should be lifted by spin orbit coupling, it doesn't need to be strong. You can still have it in that context. And then what I hope I can illustrate to you as I go through this talk, actually, there are many different ways to make these kinds of topological phases. It was historically that people first thought about this heavy spin orbit coupling. So that is an excellent question. If you get really bored during my talk, which happens quite easily, so something I will advertise is that there's these things now called topological materials databases. So this is what I do when I get a little bit bored during talks, is that if you just Google search topological materials database, and it'll show you can search around for thousands of different kinds of topological materials. And you yourself can see how many of them are composed of light elements, heavy elements, and so on. So that's it. You could probably even look up these particular ones and see. So that's a great question.
Great. One more question is it okay if we take a screenshot of your talk for social media for the PCCM? We forgot to ask.
Yeah. So as far as I understand, this is going to be in some point even posted on YouTube.
Right, it'll be uploaded online, but I guess just now for the.
Sure. Yeah. No. There's nothing I can do if it's going to be on YouTube, right? So please, as much as you like, and of course you have.
Great,
Please.
Thank you.
Okay. Yeah. Good. Okay. So those are excellent questions. So right. So how would you make one of these materials magnetic? So it turned out that these kind of workhorse topological materials, whether antimony telluride or bismuth telluride, a lot of them had been explored in the context of magnetism even prior to the understanding that they could have interesting topological phases. And it was in a different and interesting context called dilute magnetic semiconductors. And so here's an example of, by making these systems magnetic, you take these small gap semiconductors and really you just try to force in some transition element using doping. You know, basically the way you do it is when you're grinding up your antimony and these powders together, you sprinkle in a little bit of some transition element. And as long as you grow the material in the right way, so that, for example, you can integrate actually here's some of this chromium and antimony telluride, you can make a magnet with some reasonable Curie temperature, 10 Kelvin, 20 Kelvin, 30 Kelvin. So it was possible even early on to bring in magnetism to these systems. And so then you could ask the immediate question, so how does that manifest itself in this surface mode? And so this was an experiment done by the group of ZX Shen, and this was very early on where, for example, I think this is all bismuth selenide. So here's bismuth selenide, and they're examining this Dirac cone. And in the pristine bismuth selenide, there's no evidence for a gap. They put in some elements, so this might not be obvious, but you would not expect there to be magnetism associated with this thallium. I don't know, it's particularly toxic. I'm not sure exactly why they chose it. Maybe they're showing that topology doesn't care about toxicity. I don't know, but they put in a bunch of this thallium and there's no gap. But then amazingly, when they dope in iron to some significant amount, they do see spectroscopic evidence that there is a gap opening. So it's not telling you what's going on inside of that gap yet, but it is a very early indication that you could modify the topological protection of this gap just by introducing a magnetic element. And even an interesting nuance in this system is that iron doping into bismuth selenide when it's in the so-called conduction band doesn't even give you ferromagnetism. But it's just the notion here was even just a fluctuation of this magnetic spin would be enough to give you what was a pretty sizable gap. So I'll step forward a little bit, a few years to what was really a crowning achievement in this field, which was, in my opinion anyways, really a true marriage of magnetism and topology in this experimental discovery by Yayu Wang and Shikun Shui and others at Tsinghua University, where they managed to make, instead of bulk crystals, these were thin films, where they could put a really significant amount of chromium, which would be magnetic, into not exactly bismuth selenide, but it's like bismuth, tellurium, selenium. It's anyways related to this family of these TIs. And what they found in this system was when they measured the electrical transport at very low temperature, just like a little bit just like that graph I showed you from Wikipedia with a quantized Hall response, they also saw a quantum Hall effect. But instead of being that kind of staircase driven by an external magnetic field, now it looked like a ferromagnetic hysteresis loop, because the way that the quantization was responding was the way it was responding to the ferromagnetism associated with these chromium ions. And it was really, I think, a fantastic achievement, which demonstrated to the field that you could combine these two extremely rich areas of condensed matter physics, magnetism and so, for example, quantum Hall physics, into one animal, right? And I think that was, for me anyways, particularly exciting because, as I sort of mentioned to you before, one of the great things about magnetism is that often it can lead to these very useful things. It can be a very robust effect. This particular experiment in the beginning was done at very low temperatures for reasons I'll tell you in a moment. But I think a lot of people were inspired to think that, wow, we could maybe realize these very robust and important effects in these systems. So something I will mention about this field is that actually, I mentioned that experiment was in 2013. Really, in the early days of this rebirth of thinking about topology and condensed matter, it was already, from a theoretical perspective, really clearly predicted that you should be able to get, by combining magnetism and topological insulator, this kind of chiral mode. And not only could you see that from electrical transport, there was also other predictions of optical effects you can see, which later came several years later. So sort of one way of posing from a materials view is sort of what took so long? Right? Why was it so difficult for us to achieve these effects? And that question was largely answered when our friends with the sort of real space scanning techniques came and started examining these materials. So this is an example of two different scanning techniques on two different kinds of magnetic topological insulators. So this is pretty much the same as the original material in which the quantum anomalous Hall effect was discovered. So you're putting chromium into a thin film of bismuth antimony telluride. This actually is a single crystal of a very similar system. This is a real space scanning squid. This is a STM experiment. And basically what you find, I'm sorry, the scale bars might be a little bit hard to read. The point is these materials are a mess in terms of real space. So we had this notion that we were doping some transition element into these systems, but really it's like alloying. And it's not totally obvious why this extreme level of disorder necessarily means you have to go down to below 100 millikelvin to see these effects, but it was a clear evidence that that was really a shortcoming of these systems. Can't tell if Nick is giving me the high sign that there's a question.
Yeah, we have another question,
Yeah.
if you don't mind being interrupted.
No, not at all.
So Jashin Yin has asked if the iron doping seems to be surface doping rather than bulk in the science paper, and if so, does the iron dope onto one surface of the, so if the iron dopes onto one surface of the TI, how would the Dirac cone on the other surface respond? Would it open again?
It's super, super interesting. So I will say, so if my recollection of this paper is that these were grown in like a bulk method. So really the whole crystal has iron in it. Now, and I think so therefore, the iron was everywhere. There's nothing you can do to get rid of it. But you can definitely do the experiment you're talking about, especially using these modern techniques in photo emission where you spray magnetic ions on one surface and not the other. And there was a really long theoretical debate about whether or not you could physically imagine disconnecting those surfaces. So what I can say is that there is now, from a perspective of a transport experiment, I think this is a paper you can find on archive from my previous colleagues, led by Yoshi Takura and his colleagues, where they grew thin films where they only dope these magnetic ions on one half of the film and not the other. And it really indeed looks like you basically affect one surface and not the other. Is that you can affect the Dirac cone on one surface, but not on the other surface. So spectroscopically, I don't know if that has been demonstrated with the deposition of magnetic ions, but I would imagine that's something that could also be probed. But in this early paper, this was a bulk doping. So it's a great question. It's the kind of thought experiment questions we were all asking in the beginning. Like, could you do this to one surface and not the other? How would that work? So it's a great question. I encourage you to look at that paper from the group of Takura. It's very, very interesting. Okay, so speaking of which, I was mentioning all the shortcomings of these kind of materials, but mentioning the kind of unusual thought experiments you might be able to do. Again, this group that I previously mentioned was able to do amazing things, like even in these relatively disordered systems, go in with a little magnetic MFM tip and write little areas where you could reverse just one part of the magnetism to have one domain with another. And then they showed basically that around these little edges, you could trap these little chiral modes, right? So even in these relatively disordered systems, you could do the kind of amazing things of manipulating quantum Hall systems with magnetism that we all hoped would be true. So let me sort of zoom out then a little bit. So how could you make these materials better? This is from a review article where basically they showed the development of being able to control these materials better and better. So this was sort of the first example of chromium doping into these systems. Later work was done changing from chromium to some different magnetic ion. But really, some of the most beautiful work came from leveraging some of the degrees of freedom that you get in thin films, which is basically being able to modulation dope these systems. And by modulation dope, although that's not exactly, some people might argue what's being done here, anyways, you're selectively putting chromium into one part of the film. And what they showed by doing that was that, at least in a very rough picture, you can imagine they're keeping the film pristine in some areas and sort of confining the magnetism to other areas. And what they're able to do amazingly is bring the sort of effective temperature at which you could see this quantum Hall effect or some remnants of this quantum Hall effect to 30 millikelvin to something like 2 orders of magnitude higher in temperature. Right? And it's amazing through this kind of heterostructure development how much this could be improved. And at the same time, I won't show a lot about this. A lot of people are thinking about using van der Waals materials to do very similar things, right? Being able to sort of put together different layered systems in this way. So this is a big sort of growth direction. If you're looking for something to think about in the future, how to make these interfaces better is a real key area. Yeah, I can't tell, Nick. Yeah, you can give me a thumbs up when there's a question. Yeah.
Oh, sure. Yeah, you can see me, right? Yeah. Okay. So
yeah.
we have an anonymous question as, is it possible to have a material that is not a TI, but still conducts only at the surface? So I guess it's like a TI type behavior without actually being.
Absolutely. Yeah. So excellent question. So, right. So can you have what I would call conventional boundary modes? And the answer is absolutely yes. So it's been known for a long time, particularly in semiconductor structures, that basically where the chemical potential sits on the surface of a material isn't necessarily where it sits in the bulk of the material. And this sort of prefaces a quote, if I have time, if I ever get to the end of my lecture, of Wolfgang Pauli that said, "God made the bulk and surfaces were invented by the devil." That surfaces are not well controlled typically, right? And so it's very important to be able to distinguish between conventional surface modes and topological surface modes. And there are different ways of doing it. So one spectroscopic way is that, for example, in topological insulators, if I go back a little bit, and I didn't mention this, so I'm glad it was asked, you do expect a particular kind of winding of the electron spin degree of freedom, which in principle should be able to help you distinguish this type of surface states from others. Other ways of being able to tell that is, and I think the real hallmark that people believe is when your boundary mode, in this case, it's a 1D boundary mode, when it's quantized, when its conductance is quantized in fundamental units of h/e², what it tells you is that you're measuring the topological band index of your state, and that can tell you definitively that it has a topological origin rather than a trivial origin. So, but that is definitely, and you can actually have a co-mingling of these two types of surface modes, right? So these are all excellent questions. Perhaps one of the reasons that this experiment had to be done at very low temperature is that coexisting with these exotic surface modes were more conventional types of surface modes that needed to be Anderson localized by going to extremely low temperature. So these are all really good questions. I do realize the questions mean that there's no
Mind if I
home
ask
model.
one more question?
No, do it. Let's do it. Yeah.
So Chun-Li Huang has asked, what is the mechanism for the longitudinal resistance being not equal to 0 in this material? Maybe you can.
So I guess, I suppose this material, do you mean like in this particular one, or what are we talking about?
Yeah, I'm not sure. It says this material, but
Okay. So I can say that, so let me know if they clarify. But what I will interpret that as is that, what's interesting in these systems is that at a relatively high temperature, so it's not really shown here, you see this hysteresis, which is not quantized. But clearly it looks like there's still some signature of the chiral edge mode. And it's not until you go to extremely low temperature that the resistance finally goes to 0. And what seems to be true in these systems is that if I sort of show it here, here you have some sort of chiral mode, and it's that mode exists, but it's that there are still other bulk modes. And those could be trivial surface states, those could also be bulk states, and they're just not frozen out yet. And you have to go to lower and lower temperature to really remove them. And what seems to be true empirically is you make the materials cleaner and cleaner and better, you remove this remnant bulk conduction. But it's anyways the idea that you can have parallel channels at higher temperature, which you eventually freeze at lower temperatures. So yeah, good. Right. So what are other ways you could do this? So instead of doing some doping or modulation, there is now a whole direction where people are trying to sort of realize materials which just intrinsically intermix magnetism and topology. And so this is one example which has been around for a while. Can't tell if there's a question from Nick.
There is another question. We can save some to the end too.
Okay. So I'll leave it to you. So Nick, but really just like break in when you have a question.
Sure.
And then I'll stop trying to read you.
Okay, might as well ask this one while I have it up, I guess. So Laurel Anderson has asked, is there any advantage to bulk doping versus surface doping versus creating a layered structure like using van der Waals materials?
Yeah.
The magnetism and TIs are the top materials.
Yeah. So there's different ways to look at this. And I would say that there are many ways to try to approach making this really interesting combination of magnetism and topology. And I think there are pros and cons to these different structures. So, for example, if you do something like surface doping, the advantage is that, especially if you do this in some vacuum system, you can put on as many magnetic ions as you want. There's sort of no limit to how much you can spray on the surface, right? And so, but at the same time, it will only gap your top surface. And for example, it won't affect the bottom surface. Also, maybe you add a lot of disorder to the top surface when you do that. This technique, which I mentioned here, I think a little bit splits the difference there, where instead of doping everywhere, you kind of dope in some specific places. So I think this is good, but because it's still grown at a finite temperature, these interfaces are not atomically sharp. So you still get some bleeding of the chromium ions away from where you really want them. So using van der Waals materials, you would then overcome that disadvantage because those are atomically sharp in the sense that just at room temperature, you put them together and there's no intermingling across the interface. The negative point to those systems, though, can be that it can be hard to get a lot of good magnetic exchange across that interface, meaning how much do the electrons in one layer really feel the magnetism in the other layer. So this is the reason I was so excited to answer that question is it segues into this other approach of the problem, which is just finding kind of natural materials which can try to intermingle those two types of layers. And that is, I think, one way of viewing this manganese bismuth telluride. So there's actually many variants of this compound, depending exactly how you layer them together. This is the so-called 1-2-4 variation, where you can really imagine just taking bismuth telluride, so these 5 layers of tellurium bismuth, and inserting a layer of manganese telluride. And this manganese telluride, at least within this one layer, is ferromagnetic. And the thing which slightly complicates this compound is it turns out in this 1-2-4 variation, from one of these sets of 7 layers to the next, there's an antiferromagnetic coupling. But anyways, it itself is a very interesting object, so-called antiferromagnetic topological insulator. And I have to sort of start to summarize this at some point. the most recent excitement in this compound is that you could imagine, okay, it's antiferromagnetic if you've got this big structure, but I could see that in one of the unit cells or part of this unit cell, there's 5 layers. So that would seem like even if it was antiferromagnetic, in principle, it seems to still have kind of a net moment. And that might be connected to realizing something like a magnetic topological phase. And very much that was what was realized very recently, that if you could isolate using these exfoliation techniques, just, one of these, this is 7 of the layers, but if you stack an odd number of them together, you could realize something that looks a lot like this original quantum anomalous Hall effect, but in this intrinsic material. And indeed, compared to this original experiment done at 30 millikelvin, this is at something like 1, 2, 3, 4, 5 Kelvin, where you can see this kind of quantization. And I would just mention in passing that, from my opinion, once you see it, especially in 2 systems, it's kind of this material science by induction, where if you see it in 1, I don't know, 2, by the time you see it in 2, it should be seen everywhere. In the same issue, as it turned out, there was the same kind of realization of the quantum anomalous Hall effect, but you could not get a more different magnetic system. And this is twisted bilayer graphene, which is next to hexagonal boron nitride, where magnetism arises not from local moments, but so-called orbital ferromagnetism. And in this case, again, you get this quantum anomalous Hall effect. It looks different because there are these kind of so-called Barkhausen jumps in the way the magnetic transition happens. But fundamentally, the longitudinal resistivity value is the same, right? And so it's amazing that these 2 very disparate systems connect to the same topological ground state. So that's one place I try to end that the part of the talk. There's a lot more I could say. I'd be happy to answer other questions. I realize I have no hope of finishing on time. But that's fine. I really would rather have the questions than me get through all these things. So again, more I could say about that topic, but let me transition a little bit to talk about a different topological object, this topological semimetal, and how it interacts with magnetism. So this is a more recent development, this object called the topological semimetal. And what you can imagine is that there are different variations. I'm going to focus on one called a vial semimetal. But at the most simple type, in my opinion, a topological semimetal is what people call a Dirac semimetal. And so the language some people use is that it's like a 3-dimensional version of graphene. And so what they mean is just that, graphene, I think we all understand, it has a linear dispersion. And the idea of a Dirac semimetal is it has a linear dispersion in every direction. So, and it's not that the Fermi velocity has to be the same in every direction, but it has this kind of linear dispersion around some points in momentum space. And so you can make these a lot of different ways. One way to make them, and as was originally proposed, is take basically a system where by some tuning parameter, you can go from a conventional insulator to a topological insulator. So through that transition, you close and open the band gap. And at that band touching point, you have a Dirac semimetal. So a variation on that is if you break a symmetry in these systems, time reversal or inversion symmetry, you split this Dirac cone into what we call 2 different vial cones. And these 2 vial cones themselves, then, for example, in the bulk are interesting. They host a lot of, there's Berry curvature associated with those points in momentum space. But perhaps even more interestingly, when you go to the physical boundary of those systems, they also have a kind of topological feature, but it comes in the form of the so-called Fermi arc, which connects those points in K-space. So it's a very different animal than the original topological insulator. First of all, even in the bulk, there are interesting modes, which are really sourced near these momentum space points. But then at the surface, they terminate in these beautiful Fermi arcs. And the inversion breaking type of this material, for example, tantalum arsenic, was very soon after these predictions demonstrated in a very beautiful way by a photoemission spectroscopy. So the idea is that this is kind of looking at the bulk electronic structure, and it is indeed characterized by these points, right? And there's these points in momentum space. There are actually many points because it turns out one way of thinking about it is for almost every symmetry you have in a crystal, you end up doubling the number of these vial points. But then, for example, what you can look at is the dispersion. If you look at the energy dependence around these points, you can indeed see they have these linear type crossings. And then when you go look at the surface, you can see these arcs, and these are Fermi arcs, which are basically on the surface connecting these vial points. So it was really just as was expected. And really, in the spirit of this field, it turns out there wasn't just these type of vial systems. There's other types. There's type 1, there's type 2, which basically have different kinds of tilting of vial cones. There's types which are not only driven by this inversion breaking, but to couple back to the theme of my talk, also types which are driven by time reversal symmetry breaking. And I think the appeal that you might have of these magnetic analogs, which are driven by time reversal breaking, is that you could imagine by, basically the big picture is that the position in momentum space of these magnetic vial points, I should say, is dictated by the nature of the time reversal braking. So just in the same way that in the topological insulator, the magnetic topological insulator, you could change the chirality of the mode by reversing the magnetism. Here you could change a very rich magnetic structure also by changing the magnetism. So it took a little bit longer to find these magnetic variants, but the last 1 or 2 years have seen more and more examples of these so-called magnetic biosystems. So this is just one particular example I particularly like. It's a material called cobaltine sulfide. And what it does is it has these ferromagnetic layers. And the magnetism may be a little more complicated than was originally thought, but nevertheless, it's a pretty good magnet. Magnetizes around 175 Kelvin, has a nice magnetic hysteresis loop. And in terms of electronic structure, these are just calculations. I'll show you the data in a moment. What was predicted was that you should get these kind of vial points, sitting in a K-space. And these vial points, among other things, can contribute to the transverse conductivity in a way that is related to what you see for quantum Hall physics in 2D, but it's sort of a 3D analog of that. And for example, you do see a large anomalous Hall effect in these systems that arises one way or another from these vial points. So in terms of these spectroscopy, these were very challenging experiments, but were recently done. And for example, which you can see, this is a combination of looking at a calculation and then photo emission. These sorts of Fermi arcs that were expected to be seen on the surface were observed. And then these sort of vial points, here this was, I think, done aided by doing some surface doping of potassium. You could also see these kind of linearly dispersing vial points. So it's really just a demonstration that indeed magnetism can drive this kind of vial electronic structure. And for completion, I would mention also there were beautiful experiments done by STM, which also showed through quasi-particle interference that you could also see these things. So this is a very, very rich area that I have to admit I'm going over very quickly, just in the spirit, just in order to be able to cover a little more ground. But one thing I want to mention, and then I'll try to get to more in my second lecture, is that there are really deep connections between the first part of my talk and this part of my talk, in the sense that there are ways of imagining constructing vial semimetals from magnetic topological insulators. And this was a beautiful work done by, with one of the authors is the next speaker, Professor Leon Balentz. And he showed that a way conceptually of building a vial semimetal, and basically an ideal vial semimetal, was layering magnetic topological insulators together with a type of insulating layer stuck in between. And one way of thinking about how this works is that this insulating layer and also the thickness of the topological insulator layer, you're basically controlling how much coupling there are between these different surfaces, either between the surfaces of the TI or from one TI to the next. And if there's very little coupling between these surfaces, you're in this part of the phase diagram, and they refer to it as a quantum anomalous Hall phase because you've basically decoupled the layers. And then you could basically imagine sort of covering up the coupling from one of these magnetic TIs to the next, and they act just like the quantum anomalous Hall phase from the first part of my talk. If you make the couplings way too big, either between the surfaces of one or the other, you drive the system into some trivial regime, which is just insulating. But there is an interesting middle ground where there's a sort of an intermediate coupling where you realize a vial semimetal. Nick, is there a question?
Yeah, we have a couple questions.
Okay.
I think we could leave them to it depends on if you want to answer them now or at the end.
Okay, so you know what I'll do, just because if I answer them now, I'll go way over. Yeah, so why don't I'll just try to get through as much as I can in the next 10 minutes to roughly end on time.
Sure.
And
yeah,
then
you
we can
go
take
over a little bit too. It's no big deal.
Sure. Okay, so but okay, good. So then why don't we hold them and then I'll just answer them at the end, because otherwise we'll be here till 2 o'clock or something. I'm sorry. So okay, so and I think so. What let me say about this is that there's another interesting thing, which is that I think the fact that there's this deep connection between these two systems, I think it can actually help you discover more examples of either vial or quantum anomalous Hall systems, because if you find one, I think it can give you a design principle to imagine finding the other by finding ways of either more or less coupling the layers together. But I'll say more about that in the second lecture. So let me just take the last 10 minutes by giving you, I think, an example of, I think, an interesting thing you can do, which is thinking about, okay, for example, in the context of these vial semimetals, I mentioned there could be an inversion braking type, there could be a magnetic type. An interesting question that I think a lot of people wondered about and we pursued in a particular way was, well, what happens if you try to mix both of these things together? Is that interesting or not? So the material context which I want to work in is these compounds called the rare earth aluminum germanides. And what they are is, even with a non-magnetic rare earth on this site, these are expected and were shown to be vile semimetals. And the point is that they have a screw axis. I don't know if you would remember 50 minutes ago at the end of the animation I was showing you, the atoms were moving in this screw type fashion. There's a so-called 4-1 screw axis which runs through this crystal. And what it gives you from a prediction and then from these photo emission experiments are these vile type crossings. And they're unusual crossings. They're this so-called type 2 crossing. There's also type 1 crossings. But because this is a rare earth system, not only could you put lanthanum on this site, which is non-magnetic, you could use one of the magnetic rare earths. And the thing which makes this system, and the title I hope sort of gives it away, is that not only can you introduce magnetism into this system, it's relatively complicated magnetism in the sense that it sits on a lattice which has a relatively low degree of symmetry. So, to be honest, even when I give a talk in person, I have to give a lot of body language to get across this notion of a screw axis. So this slide might be a little much, but I'll show you the magnetic structure in a moment. So the idea is that the system has a set of 4-1 screw axes, which, if you look in the tetragonal plane, sit at these points. And so I've colored here this rare earth atom in 2 different colors. It's the same atom, but what I'm trying to show you is the atom before and after this symmetry operation. And what's interesting about this system, and this is really getting into the weeds, is that the site symmetry for each of these atoms is orthorhombic. So it's actually the local XY axes are allowed to be different in this crystal. And what it means is that when you do this 4-1 screw operation and you move from this position to this position, what you do fundamentally is rotate that local XY axis. And it means that basically, if you have a spin, if you have some, for example, antiferromagnetic spin ordering between these 2 sites, even if the spins are antiferromagnetic, the moments will be ferrimagnetic, meaning the spin sizes can be different. So that had to be honestly explained to me over and over by the next speaker, Professor Leon Valence, till I finally understood it. But the upshot was that it was a way of understanding how the magnetism in this system can be a so-called ferrimagnetic ordering. So, okay, look, I think a priori, you can definitely be asking the question, why is this guy talking about this weird magnetic structure for 2 minutes? It seems to be uncoupled from, but what I want to demonstrate to you is that even this kind of complex magnetism, when you bring it into some topological system, can give you some interesting and I think a surprising behavior. So just to get into the details a little bit, in order to confirm such a structure, you have to do neutron scattering. And what I will say just in brief is, by doing this elastic neutron scattering, we could really show that, what was the really most likely magnetic structure in this antiferromagnetic phase for this particular material was this kind of ferromagnetic order, and it could be characterized by all of the symmetries shown here. So why were we interested? So we were interested because when we examined these crystals, so here is a crystal, and this is showing the tetragonal plane. What we did was an experiment, which is very standard in the world of magnetotransport, and that what we did was we ran a current along one of the in-plane directions, and we rotated an in-plane magnetic field. And above the magnetic ordering temperature, it looked very conventional. And so I didn't tell you before about how these systems typically behave, but typically there's some symmetry allowed series of cosines, which you can expand this response. And yeah, pretty much it looked like some series of cosines. But for whatever reason, when we went below the magnetic ordering temperature down to 2 Kelvin, superimposed on top of this, we saw this huge and very sharp response, which was really at the time unlike anything I had ever observed previously. And the solution to where this came from, this was a great, a lot of conversations between Lucille Savary, who was an MIT postdoc at the time, is now a faculty member in France, and Leon, who is, again, speaking next, was through understanding how, in a different way, topology and magnetism could give rise to a new kind of magnetotransport effect. So let me walk through you the picture we have of how this works. So in this system, you have at low temperature this ferrimagnetic ordering. And so if you imagine in zero field, this is what, or very low field anyway, with field along this, say, 100 axis, this is what the magnetic order looks like. So if you apply a huge magnetic field along 100, eventually you're going to flip the moments, right? I mean, eventually the moments will give up and flip. And an interesting thing is that at some intermediate field, the spins will go through a so-called flop transition, where it turns out they can lower a little bit their energy by flopping, so that they now agree a little bit with the Zeeman field, but retain some of the exchange, the sort of ferrimagnetic exchange. And the interesting thing in this system is that because the spins are imbalanced because of this ferromagnetic ordering, you have a little bit of transverse magnetization associated with these two types of magnetic orders. And so in the case where you have the field aligned exactly along 100, and you turn it up and go through this transition, the energy of these two magnetic states is the same. And so in the context of magnetism, which you would then immediately understand, is that then I will get domains of those two magnetic orders. However, if I tilt the field just a little bit in one direction, as I go through this transition, I will again go from having spins all this way to spins all this way, but the energy of these two states is no longer the same. And I actually favor one of the magnetic domains. That would also be true if I was tilted a little bit the other way. So this series of transitions you go through by having a slightly tilted magnetic field only involves sort of half of the magnetic degrees of freedom. And you only get these two states having the same energy when you're precisely having the field aligned along this direction. So it's kind of like a symmetry allowed a magnetic state. And in this state, you have a huge number of magnetic domains. So what's interesting is that that seems to couple in a very deep way to the topological aspects of the electronic structure, because then if you consider in real space a magnetic domain, which you have when you go from one magnetic domain to the other. So in real space, you have a different magnetic pattern. But in K-space, because this is a Weyl system, the position of the nodal part of the electronic structure is different in those two real space domains. And so when you imagine getting to a very nodal band structure, so here it's not so nodal, you imagine doing the quantum mechanics problem of an electron tunneling across this domain wall. As the Fermi surface becomes more and more nodal, you'll end up having a smaller and smaller overlap between these two domains, and the ability for an electron to move from one domain to the other will become more and more restricted just from this picture of sort of basically conductance across the domain wall. And so then what you can finally couple to think about the Weyl points in the system is this was a beautiful part of a calculation done by the co-authors of this paper, where they showed that, for example, without thinking about the magnetic order, the Weyl nodes would be in one position. But then upon having one domain or the other, the Weyl nodes move in K-space, right? And it was the ability basically to tune the position of the K-space Weyl nodes that you could tune the overlap between them, right? And it seemed to be that could be what was responsible for this big response. So this can be depicted in different ways. This was a very nice depiction people made related to this article, where they're sort of showing the difference between the resistance in this direction had this notion of the real space magnetic structure and the sort of the allowed electron momentum in XY space. And if you want to, if you have a very optimistic view going forward, one thing you could think about would be that, so what is the utility of having this very sharp angular sensing? If you look at sort of how ordinary magnetic systems behave, typically you have this sort of smooth sinusoidal responses, for example, in this magnetic permalloy to external fields. What you could imagine is that in principle, what you could build here is a new type of way of doing like a vector magnetic sensing. So if you want me to say something crazy and unrealistic, imagine growing this material like on the surface of a sphere or something like that, right? And basically what you would be able to do is pick out, the vector orientation of a magnetic moment. So that's a fundamentally different way of doing magnetic sensing. So at the moment, the system we made is made out of mostly cerium. So this only works at 4 Kelvin. Okay, not so good. But you can imagine trying to engineer a structure which really just follows these symmetry rules and tries to have a topological band structure, but it is made out of maybe a transition element and pushes all this physics to a higher level. And this is a plot I showed before. Maybe the same way that GMR could change the way that you did magnetic sensing of bits. This so-called SAMR might have some way of changing the way that we do, vector magnetic sensing. So what I will leave for the afternoon is, as I said, the second topic of magnetism and topological metals. So I will just give you I think just like really 1 or 2 slides of outlook, and then I'm very happy to take questions next. So what I will try to leave you for with context sort of halfway through these lectures is the challenges that you might have for trying to use topology for something useful in the concept of electronics. And I already mentioned that if you're a pessimist, you could follow this statement that is attributed to Wolfgang Pauli, that God made the bulk, surfaces were invented by the devil, that a lot of times the topological modes that we're interested in might be intermingled, as was already asked, with some conventional states and hard to disentangle. But if you're more of an optimist, Herbert Kromer, who won the Nobel Prize for thinking about things related to, for example, the high electron mobility transistor, said that the interface is the device. meaning that what's most important for a lot of device applications are the states which are at the interface. And a lot of these exotic topological boundary modes are pinned to the surface. And I think the nuance, which I've been trying to add through my presentation, is that it might be that magnetism offers a key handle to be able to turn these interesting topological modes into something that you could use more like a device. One thing I just want to mention before wrapping up, and I didn't get to touch on at all, is there is something related to magnetism and topology. There's a whole area related to so-called topological spintronics. I'm just borrowing these slides from Nitin Samarth, who is a professor at Penn State. And so he and others have been leading the charge in understanding how things like topological insulator could be useful for spintronics from the perspective of the so-called spin Hall effect. So just in a minute, let me try to describe to you, and I hope you could follow a lot of these references. So something that's very important in the field of spintronics is the ability to use some heavy element materials to deposit spin angular momentum into other materials. And there was a revolution recently where they realized systems which have a so-called large spin Hall effect, systems where when you have a spin current, the two opposite spins will move in different directions, perpendicular to the direction of motion, that you could use this motion from the spin Hall effect to deposit spin angular momentum into, say, a ferromagnetic layer that was sitting atop this material. And in terms of their performance, there's different ways of characterizing them. One way is the so-called spin Hall angle. And the amazing realization a few years ago was these very conventional topological insulators like bismuth selenide appear to have a huge performance, a very large spin Hall angle, which I think is not particularly well understood, but is certainly appreciated and recognized in this subfield. So it could be that this concept might have very deep roots, and in this broad array of topological materials could even be another way of bringing these materials to bear. It's just something I didn't have time to really touch on, but I wanted to advertise. So this is just my group, which has helped me understand and think through a lot of these questions. That's all I had for the first talk. I would love to take any further questions now.
Yeah, thank you so much, Professor Checkelsky. It was a really great talk. Learned a lot that I thought I already knew, but it's great. Yeah, we have about 5 or 6 questions here we can go through. Plenty of time to answer them. So some of these go back to earlier in the talk. Okay. One is, what is a mechanism of magnetism in the bismuth SB chalcogenides? Is it, if it is RKKY mediated, as in carrier mediated, how is it possible to tune the Fermi energy to the band gap and have magnetism?
Yeah. So there, what I will say, especially because I know this is recorded, is that there is some controversy, or anyways discussion, about the origin of magnetism in these systems. And I think somewhere I even tried to hedge my bets by mentioning that it's either this RKKY manner, or other people have talked about a valence electron mediated magnetism, a so-called Van Vleck magnetism. So I think there is evidence for both possibilities. I think one way of understanding how it could even arise in the context of RKKY-like interactions is if it was still driven by the surface electrons in these systems, right? So what you could imagine happening is that if you have this surface spectrum, if you even forget about bulk magnetism, you could have a magnetic instability on the surface by which, if the Fermi level is, for example, inside this gap, you could get ferromagnetism driven just by the electronic energy gain of the surface electrons by being able to open a gap. So that is one particular view. I mean, I stick to that because I had done some experiments that were partly supportive of that picture. There's other pictures which are associated instead with just a bulk-driven magnetism from this Van Vleck paramagnetism. It seems like, in terms of a theoretical framework, both have the ability to drive magnetism in these systems. So I think, yeah, that's what I can say. I think in both cases, you can imagine them giving rise to this type of effect.
Sure, great. Next question is, in cobalt tin selenide, is the carrier density 0 at the Fermi level?
So I think cobalt tin sulfide means this one.
Yeah, sorry.
Yeah, good. So if you had an ideal vial semimetal, if I can maybe show a picture of, like, maybe here. Yeah, what you would really want is to have the Fermi level. It's not obvious. So one way of thinking is what you would really want to have an ideal case would be to have the Fermi level right there, only cutting across the two Dirac cones, or vial cones. And what I will say is that, for cobalt tin sulfide, the answer is no. I mean, the great thing is that these crossing points, which are sort of hidden somewhere here along some non-high symmetry direction, they are pretty close to the Fermi surface. But admittedly, there's even another band here. But what I will say is that, originally, I think coming from the background of topological insulator, immediately, previously there, we always really wanted to have this Dirac cone right at the surface, but it's not obvious if that's always necessarily what you really want for vial semimetal systems. So, for example, there's a lot of interesting electronic effects which have to do with transitions on vial cones, which actually really require the vial cone to be quite far away from the Fermi level. So even in systems where they're not pinned to the Fermi surface, you can still get a lot of the exotica that you're after. However, if you're a transport person like me and you want to see a big anomalous Hall effect, yes, those things should be pinned near to the Fermi level. So as far as I know, there has not yet been found this perfect, which you might call ideal vial semimetal, which, for example, only has vial nodes at the Fermi surface, or maybe more to the point, only has maybe just a single pair. Even in this cobaltin sulfide, you have more than two. But it's really still very much a fantastic compound.
Yeah, great. Cool. Another question is from Chun-Li Huang again. Are there spin waves, like measured from neutron scattering, in the high temperature paramagnetic phase of magnetic wild semimetals? He says that he's drawing an analogy from short range order in a conventional itinerant magnet like nickel.
Yeah, so there hasn't. I would say there's a lot that could be done. I mean, yeah, surely to try to understand the magnetism in these systems. I am not aware of those type of experiments, but what I can give you as a pivot, and I think why a lot of those experiments may be underway, is that almost everything I've talked about so far in the context of interesting electronic band structures and those types of modes, there's topological analogs for magnetic electronic structure, if you want to call it that, or sort of magnon modes. And so I think a lot of interest in these systems would not only be to understand the fundamental magnetism in these systems, but you could actually look for the equivalent of sort of like a boundary spin wave modes and sort of some sort of topological magnon insulator or something like that. So there is a huge amount of interest in those systems, but no, I don't know any specific examples of the kind of experiment that you are looking for.
Sure, cool. Another question is, are there magnetic domains in the rare earth aluminum germanium system directly imaged under different magnetic field with a certain technique?
No, so that immediately would be the question that, yeah, so that's 100% the thing that we're trying to do. I mean, I have to say, I hope we're the first to do it. Yeah, but that's certainly what we should be trying to do. In terms of our estimates, it seems like the magnetic domain size could be on the order of like hundreds of nanometers. So that actually lends itself very well to a variety of techniques. So in principle, scanning MFM, I think, should have a shot at being able to measure this. You have to think carefully about what an MFM is sensitive to. We think along the right surface that it would be sensitive. Really, part of the challenge just comes from the low magnetic ordering temperature. It orders at 3 or 4 Kelvin. Definitely those tools exist. There are just fewer of them. You might also hope that maybe STM, if you could do some sort of spin polarized STM, might be able to do that. That might be. I don't think it's that's too large, but that's definitely the next step. And what you'd really want to be able then to image is maybe some kind of interesting electronic state which lives along this magnetic domain.
Yeah, I actually had a question about the magnetic domains before. When you have the singular angular magnetic resistance, yep, is there any effect from like the fact that the magnetization is different in the different domains for the electron, like for the change in resistance, right? There's different mechanisms that could cause magnetoresistance from domains, right? I don't know if there's other contributions there going on.
Yeah, no. I mean, so certainly in this, right. So you're sort of asking like, what would the right? So it's true that also, right? Yeah, that's a good question. So when you go into this magnetic domain, it's true that the moments are tilted, right? So I think that the way that you can try to tell those two apart, because you might say like, okay, as a function of the amount of magnetization tilting, maybe the resistance could also just be intrinsically different. So I guess the way that we convince ourselves is that while that's true that there should be some contribution from the domains, is that when you think about like how little you change the magnetic field in the perpendicular direction from 0 degree angle tilt to like 0.5 degree angle tilt, you would only expect a really tiny change of the magnetic orientation. And then by studying systematically how much the magnetoresistance changes as we change the in-plane magnetic field, we can kind of rule out. So what you could probably say is that, okay, just from the tilting of the moment, you get a change that's something like this. right? You can sort of extrapolate, you sort of fit how much the moment changes as a function of field tilt angle. And really what you see is there's this additional thing on top. But you're right, just from the rotation of the moment, you would also expect this. You can also kind of see that even from this part of the phase. So this is a different magnetic structure, but here, surely what you're doing, because you're just above magnetic ordering, is you're kind of pushing the moment around, right? And so you can sort of see the scale of that effect, right? And so it's just that this effect from the domains is something that happens on top of that. But being able to image the domains would be a super important aspect of proving that.
Yeah, I want to be selfish and ask another question,
Yeah.
but there are more to get to. It's just that is there any signature of this singular angular magnetic resistance that shows up like in the Hall effect?
Yeah. So if you look in the supplementary information of the paper, yes, and it's in this kind of color plot where you show this enhancement of the resistivity at those domains, we also see an enhancement of the anomalous Hall effect, and it's not one that we can explain in the way it scales just with the magnetization, actually. And so we had a lot of different ideas about it, which we so far haven't been able to further shed any light on. I mean, it could be that just that sheet of electrons which exists at the magnetic domain, that sheet itself may carry some Barry curvature associated with the displacement of the Weil nodes and give a contribution to the Hall effect. Or it could be, it could come from some geometric texture or something like that. That's been seen in some related systems. But absolutely, there is a signature of the anomalous Hall effect there.
Oh, cool, great. Okay, I'm gonna ask some the actual attendees questions now. Pavel has asked, is the transport in the cerium, aluminum, germanium only due to Weil points, or are there additional non-topological Fermi surfaces or pockets, and may the latter affect the MR?
No, absolutely. So the answer is 100% yes, that, even from this kind of band structure calculation, for example, you can see there's an obvious pocket between gamma and X. And I think what you would want to do if you then go over to this picture about having this cross section of the Fermi surface, this effect, this SMR effect, will become more and more pronounced the more sort of, if you want to say, primarily nodal you make the electronic structure. So the hope would be, if you were looking for like a design principle to make these systems better and better, you would really want to find the maximally nodal structure. And so I think the answer is that in this systems, it's not terrible, but there are other sidebands. But I think the way I think about it is that the reason we were able to see it in this system, because it's a very general argument about symmetry allowed magnetic domains, the reason we were able to see it is because there is a strong nodality to the electronic structure in this system. But that put it on like a some many percent level of observation. But what could turn it from this to an effect which is maybe you would call giant would be being able to find sort of a cleaner type of these magnetic systems. And so the thing I would just say is that you have to combine that electronic structure, although with a sufficiently low symmetry magnetism that will allow you for this sort of domain selection effect.
Cool, great. A few more questions here. One is, could you expect tuning the crystal symmetries, like breaking inversion symmetry with pressure or strain, to tune these materials in or out of the Dirac Weil states or change the magnetic ground states?
Yeah, so so I think that's a really interesting way to think about the problem. So the way that I pitched it was, let's take the inversion breaking type, and then let's impose magnetism and see how it modifies the system. I think another way of restating your question, which is very actionable from an experimental point of view, is what if you take one of the magnetic ones and then introduce inversion breaking onto those systems or pressure. And I think that indeed that would give you an additional degree of freedom that you could use to sort of to try to further tune these systems. If they would let you, probably what you would want to do, at least in a naive picture, is you would probably want to get to a point where you have the most, quote unquote, most ideal Weil system, where you have the lowest number of Weil cones. People refer to that as kind of a hydrogen model of these Weil systems. Perhaps what lowering the crystal symmetry further could do would be to remove some of, like, for example, these duplicate cones, which arise. It would be a real challenge, I think, to take one of these magnetic ones and lower the symmetry sufficiently to get all the way down to just two Weil points. But perhaps you could use it as a tool to anyways lower the symmetry. I think that's a really good insight.
Yeah, definitely. Cool. Yeah, I think we have time for a couple more here. So I might be a little selective at first, and then if we want to answer the rest, we can.
I still have to finish my talk for 3, so just leave me enough time.
Okay.
No, I'm kidding.
Yeah, question is general question concerning noise or impurity in experimental observations. How robust are the quantized conductance plateaus of the conductance? In particular, how frequently can one see fluctuation on top of a quantized conductance?
Yeah, excellent question. So I would say that so it really depends the type of system we're talking about. If I go back to here, so these are different examples of three different examples of measuring h over e squared in these quantum Hall systems. And I would say that the present understanding is that the limitations for measuring quantization are really instrumentation in these particular examples. And one reason I mentioned that is this first report, the quantization was pretty good, but really wasn't that precise. But as really experts in the field, including, for example, David Goldhaber-Gordon's group at Stanford, came and sort of brought their high resolution tools to bear, they really showed that, so I don't think it's as far out yet as maybe the best quantum Hall systems. They showed to a very high degree of precision that you could measure quantization with these magnetic quantum Hall systems. So then you might hope that, people these days are, now that the resistance standard is based on quantum Hall, you might hope that even one day you could do that without magnetic field in one of these systems. So at the moment, I think we're a little bit far away from those systems. But in this way, I think what amazed people, if I take a step back, was that, if I go back to how disordered these systems were, this is just one measure of how disordered they are. At first, people were amazed that in a system which had an electronic mobility of, 20 centimeters squared per volt second, you could measure quantization. That goes back to the fundamental physics of the integer quantum Hall effect and the ability of some level of disorder to help you with localization at some level. So I think at the moment, even though, as far as I know, experimentally, people haven't demonstrated the same level of precision with this quantization. In that context, I think there's a strong sense or strong impression that the quantization should be achievable in the same manner in these magnetically driven phases as it is in the sort of external field driven phases.
Cool, great. I actually think we have enough time. There's just three more pretty quick questions. So one is, in cobalt tin sulfide, have there been ARPAS experiments to detect the surface Fermi arcs?
Yes. Yeah, and I'm sorry that I was running out of time at the end of my talk and I went into ultra high gear. Yes, and this is what's shown here on the left. And these were really difficult experiments as far as I can tell. I'm not a photo emission person, but I think, people knew for a long time these things should be here. And indeed, what they were able to see is evidence of both these surface Fermi arcs. And then, for example, by doping, they could bring up this Weyl point to near their Fermi surface and see this linear dispersion. And I think, it was an open question in the community because for these Weyl systems, it took several years. There was a deep appreciation that the magnetic system should exist, but it took several more years for the magnetic systems to be demonstrated from spectroscopy compared to the inversion breaking systems. And there was a lot of thought about, is that because of the finite size of magnetic domains? And to be honest, I think it just took these really, finding the right material and really doing these high resolution experiments to, I think, now definitively show that these Weyl states really exist in this system and others at this point.
Yeah, great, cool. So another one is there any relation between the number of Dirac cones in a material to its transport properties?
Yeah, so there's so I guess you're referring to Weyl semimetal. So yes, I would say that the physics I didn't touch on, which is very rich in these systems, you could definitely see, for every additional Dirac cone you have, you should basically have some additional Dirac-like band, which could contribute to transport through, for example, through quantum oscillations. There's notions that, for example, if you apply a magnetic field to one of these Dirac semimetal systems, you can split it into Weyl cones. And at that point, you could measure things like the chiral anomaly that are associated with the number of Weyl cones. You could also measure what people refer to as a quantum Hall effect, which basically measures the spatial extent in K-space, I should say, of the Dirac cone separation. So yeah, that's right. For all of these additional cones, you should affect basically some kind of multiplicative aspect. Of course, if there are different energies, then that complicates the situation.
Cool. And our final question for this first talk will be, do F electrons play a role in the transport or electronic structure of cerium, aluminum, germanium?
Yes, so it's an excellent question. So typically what thinks about in these F electron systems is normally you imagine that the F electrons, especially if it's something like gadolinium or something like that, typically the F level is pretty far away from the Fermi level and sort of locally contributes magnetism. And then it's the other electrons in the system which are associated with the conduction and valence bands, which are near the Fermi level. A lot of times cerium, that is not the case. And cerium does an interesting amount sort of mixing with the F electrons and with the conduction electrons in these systems. And you can get like FS or FD hybridization in these systems. However, it turns out in this case, what really seems to be true is that you can understand the bands at the Fermi surface really the same way as the bands from lanthanum, aluminum, germanium. So there's really not a big difference when you look at the fermiology of those two cases. So therefore, in this case, in this particular system, cerium really seems to be important for the magnetism and not as much as the fermiology that is really associated with the Weyl points.
Great. Okay. Well, thanks so much, Professor. Thanks
Yeah.
for a great talk and for answering all these questions.
My
We
pleasure.
will see you again this afternoon at 3
Okay.
p.m.
All right.
Great.
Thanks, everybody. See you
Thanks.
soon. Yeah. Bye-bye.